Could this number actually be the secret to the pyramids? Sorry, I had the wrong image. I meant pyramids like this. But still, why the number e? The number we just saw is sometimes called Euler's number, and it pops up in places like exponential growth, compound interest, and is the base of something called the natural logarithm. So what the heck does it have to do with pyramids? Well, I bet we can all agree that this shape here is a pyramid. There are actually like two-dimensional pyramids, and we call them triangles. And there's even a one-dimensional pyramid. It has a base and a height, and we might just call that a line segment. And there's even a zero-dimensional pyramid, which is just a point. I've got some more general shapes drawn over here on the right, and also the types of numbers we can assign to them. In 3 dimensions, we talk about volume. In 2 dimensions, area. In 1 dimension, length. And in 0 dimensions, because we just have points, we can only talk about maybe the number of points. So in this picture, what's the length of that line segment? Well, it's just h. And what's the area of this triangle? Well, we all remember 1/2 base times height. And maybe you even remember the formula for the volume of a pyramid. It's 1/3 the area of the base times the height. Now, math doesn't stop in 3 dimensions. It's hard to draw pictures, but we can write equations that model things in 4 or 5 dimensions and beyond. And when we write those equations and work things out, we notice there's actually a pattern. The answer we get in one step can be used in the next step, and this is the subject of something called calculus, where you might, for instance, find the volume of a 3-dimensional shape by breaking it up into a bunch of 2-dimensional shapes. And we might write down formulas like this to work out exactly what's going on. When we do that for pyramids, we see something really cool. For instance, if this is the base of a 3-dimensional period, then its area actually goes into the formula for volume. And look, we're dividing by 3. And when we work out what happens in the next dimension, the volume of the base gets in there too. And we just divide by 4, and then we multiply by the height. And guess what's going to happen in 5 dimensions? Yeah, we're going to divide by 5, we're going to have another volume, and then we're going to multiply by the height. And so the simplest pyramid you could ever write down is where all these dimensions are 1. And so if you work through like the length, the area, the volume, you're going to get these kind of cool numbers, 1/2, 1/6, 1/24. And in the next case, we're just going to take that number and divide it by 5. That's because in 5 dimensions, there's going to be a 1/5 in front of that formula. Now, if we add all these numbers up, right, we have 1, 1, 1/2, 1/6, we get this decimal 2.716 repeating. And that seems pretty close to that number e. And actually, if I just change this to a ... meaning I add up all the volumes of all the pyramids in every single dimension, I get this crazy number e. And here calculus comes to the rescue once again, because in that class you'll learn that if you want to know e to any power, you just use all those volumes we just calculated, like 1/24, 1/6, and you plug them into this formula, and it will always give you e to the x. And so yes, this thing actually has something to do with pyramids.